Hello everybody, welcome back. You ready for the exam? No, but a couple of things I did want to ask. Let's see if there was, Aiden, I know you're here, I talked to you. Is Noah here?
Yes, I'm
Yes, Noah, just see me after class, okay? Just see me right after class, all right?
Yeah.
We're going to take care of you. Okay, great, great. First I want to talk about our exam on Friday. Everybody is going to be here on Friday. Both groups A and B will be here on Friday. We do not have to worry about overcrowding the room. We've got some people who will be taking the exam. About 5 people will be taking the exam in another room. And seeing as how we can already fit the entire class in this room, that will leave us with a number of people that should allow us to really spread out, even though everybody's here. Meaning every other class is just an extra safety margin, because now we're like 12 feet apart and so forth. So 6 feet's the norm, so it should be very safe. You should bring a pencil. We will be using a Scantron form, so bring a number 2 pencil. Okay, bring a number 2 pencil. Also, once the exam starts, you will not be permitted to leave the room. Unless it's an emergency, obviously, but a casual visit to the restroom is not allowed for obvious reasons. The only way you can leave the room once we start is to turn in the exam. There will be multiple choice, there will be matching, and there will be an extra credit essay question as well. And you will leave everything attached to the exam book. I'll tear off the essay and so forth later on afterwards. So it's fairly straightforward. You should be able to finish it in the 50 minutes required. And it's on chapters 1, 2, and 3. Chapter 1, you simply need to know the 7 ideas that shook the universe. Chapters 2 and 3, there are 2 review sheets out there. There's one on Newtonian mechanics, and there's also a review sheet on Copernican astronomy. I think what I might do, if I can remember to do it, just for the heck of it, is I can email those 2 in an attachment to you as well. So you'll have them in electronic form, and you can open them up wherever you're at. But we do have a few copies still left here in the classroom. Anybody have any questions about the first exam? It only counts a little less than a quarter of your grade, because extra credits and the quizzes count too. And so it's not the be-all and end, although I can tell you that usually the average score on this first test is about a 60%. And that is because people haven't figured out that this is college and you really can't take all your time socializing, and you really do have to study. As I've said, you should be spending 2 hours for each class. That's 6 extra hours a week on this class alone. You should have been doing that since the start of the semester. If you try and cram between now and Friday, well, it won't hurt, but you can't cram like that and get all of that in. You need to make steady progress through the semester. And I know that some people are binge watching the videos. You have to learn to get out of that. You have to learn to try and watch the videos in succession. YouTube tells me how many people have watched, and if I see that less than half of the class has watched the video by the next class, that tells me that some people have not essentially been to class before the one I'm giving, and that's not a good idea. But you still got a couple of days to try and get it all together, and so give it your best, okay? I do have to talk about 2 things. One is I wanted to mention something about planets that I didn't mention, and that is that they change brightness. I had a big list out there, and I know it's listed, I believe it's listed in the review sheet, but I was looking at the review sheet, and I think we were talking about the motion of the planets and so forth in Copernican astronomy. I think it mentions in the review sheet that the planets change brightness, but I don't know if I specifically mentioned it in class. They do. Venus is so bright when it gets to its maximum brightness, people call the university and say we're being invaded or something because it is so bright. But the planets get brighter and darker. That's one of their interesting properties. All right, the last thing we have to cover before we get into new material is gravity. And Isaac Newton is generally credited with the theory of gravity. And the idea here is that we now know that there are three laws of motion. The first is the law of inertia, which states that an object will continue to move in a straight line at constant speed unless acted on by a net external force. So there are conclusions from that. If it's moving in a curved path, if it's not going straight, there is absolutely a force acting on it. There has to be. If it's going in a straight line, then you have to ask whether or not the speed is staying the same. If the speed is the same, and if it's going in a straight line, then you can conclude that the net force on it is zero. Well, the second law relates the force to the acceleration. So let me just kind of, before we get into gravity, review his three laws. There's the law of inertia, which we just described. The second law does not have a name, but it's F equals ma. And this states essentially that the same force applied to different objects will not necessarily result in the same acceleration. If you have a very massive object, the same force applied to it will produce less of an acceleration. That's because the large object has more inertia. It has more mass. It has more inertia. You take a little outboard motor for, say, a canoe or a dinghy or something, and you stick it in the water off the Princess Queen cruiser and turn it on. The cruiser will move, but it won't accelerate very much. Take that same motor and put it on something with very small mass, like a canoe, and it'll accelerate just fine. So the larger the mass, the less the acceleration. The larger the force, the larger the acceleration. That's logical. And finally, there was the law of action and reaction, which says that, this is where we sort of ended. The law of action and reaction says for every action there is an equal and opposite reaction, so that forces occur between objects, but that doesn't mean that the accelerations will be the same. If I jump off of a dinghy and step off or dive off a very tiny, tiny boat, the boat's going to fly off that way while I go into the water this way. But if I dive off again, the Princess Queen, the same force is applied to the big boat as is applied to me. I accelerate a lot, but the big cruise ship does accelerate, but not noticeably, not enough to really be noticeable. So forces always occur in pairs. Well, what Newton said was that if the sun was at the focus of an ellipse that a planet was orbiting the sun, if the planet is orbiting the sun in an ellipse, now don't make this hard, is the planet traveling in a straight line? I don't think so. Therefore, the law of inertia says there must be a net external force on that planet, causing it to go in the ellipse. There has to be some sort of an invisible force between the planet and also the sun. So if the planet is pulled by the sun is pulled by the planet. And what this means is, as the planet goes around, the sun wobbles a little bit. Now the wobble caused by Earth isn't very large, but the wobble caused by the planet Jupiter is much larger. The sun doesn't just sit there. The sun wobbles back and forth. If you watch a hammer thrower, that big ball they throw in the Olympics, they swing around like this, you'll see the person's upper body going like this while the ball goes around them. That's because the ball is exerting a force on them. Many stars have planets, and we have discovered those planets because we are able to observe the wobble in the star. So gravity, there is a force between any object with mass. What Einstein, what Newton says, and this is what's amazing, his law of universal gravitation. Now, legend has it that the apple falls on his head and suddenly he has, gravity. Well, it's not quite like that, but I can do the same thing too, or at least I can try and do it here. I can throw this up, and suddenly gravity pops into my head. No, it wasn't quite like that, all right? But this is his argument. He says that there must be a force pulling the sun towards each planet and vice versa. There has to be an invisible tether holding the planets in their orbit. And he says that tether is a force that he is going to call gravity. But when he makes it universal, he says that the same force that the Earth exerts on the sun, the gravitational force, the Earth also exerts on the apple. And when an apple is released from a tree, the same force that the Earth pulls on the sun with and that the sun pulls on the Earth with, the Earth pulls on the apple. And therefore, the apple accelerates towards the Earth. The falling of the apple is the same thing. Essentially, the Earth is falling around the sun, and just the same as the apple falls towards the Earth. Also, the moon is orbiting the Earth. The moon is pulled towards the Earth is pulled towards the moon, and that's what holds the moon in its orbit, and that's what makes the apple fall. The moon is falling towards the Earth. It's falling. It really is. We often draw orbits like this, but if I draw an orbit like this, with the sun here and the planet here, the planet is falling towards the sun. However, it's also moving sideways, so it misses the sun, falls around the sun, and like a bouncing ball, goes like this. The second of Kepler's laws that says it sweeps out equal areas in equal times, that essentially says that as the planet moves away from the sun, it slows down. This is the same thing that happens with the apple or the ball. As it moves away from the Earth, it slows down. But if it's going fast enough, it can whip around the Earth and fall again and over and over and over again. When you are on the space station, you are not, quote, truly weightless. You have almost your normal weight. You have almost your normal weight. If you want to know what it feels like when you are in orbit on the space station or in a capsule, well, have you ever gone to Kennywood or Cedar Point or Six Flags or whatever, where they drop you, and for a few seconds you feel like you're weightlessness? Well, obviously you still have weight because you're falling towards the earth. You haven't lost your weight, but it feels weightless. Well, that's great fun, right? Well, imagine if the ride never ended. Yeah, what would happen to you? I'll tell you what will happen to me. I'd barf. And it's very common that when the astronauts are first up in space, they throw up. They throw up. Your insides are not in the normal position. The food does not settle into the bottom of your stomach. It just kind of, just even talking about it makes me sick. It just kind of floats around in there. It's like, oh God, that's gonna, oh gosh, okay. Your body will adapt, but it takes a while. So gravity is universal. All objects with mass attract. There's no repulsive gravity. There's no such thing as repulsive gravity. They might have it in sci-fi, but no. Attract all other objects with mass. And this force cannot be shielded. There's no shield for gravity. So, does this mean that if there's someone down here in, quote, China or the East, are they attracted to you? Are the Himalayan mountains attracted to you? Yes, they are. The fact that there's 8,000 miles of rock between you and them does not change that. You cannot shield it. You feel pulled towards the earth. The apple falls towards the earth because every single molecule in the entire planet, including the molecules in the ocean on the other side, are pulling this towards them. And they're pulling it mostly this way. All this stuff is pulling this way. It's always towards, but when you add it all up, you're pulled towards the center of the earth. And for a typical person, that might add up to a couple hundred pounds. Enough to cause you to accelerate at 22 miles per hour per second of fall. It is substantial. It is substantial. And you cannot shield it. So yes, you are pulled towards the people in China and Japan and towards the Himalayan mountains, and you're pulled towards the Alps and they're pulled towards you and so forth. But when you add it all up, it's that weight that you feel when you stand there. That's the net force of all the objects on the planet pulling on you. And it adds up, like I say, to a couple hundred pounds. Okay? It cannot be shielded. It gets weaker with distance. So technically, there is a gravitational attraction between these two markers. Now it turns out we have apparatus here in the department, believe it or not, that can measure that force. We have a sensitive experiment here in the department that can measure the pull of attraction between these two. It's very, very tiny. And technically, you are pulled towards your neighbor, and they are pulled towards you. Everybody in this room is pulled towards you, and you're pulled towards the wall, and the board, and the floor, and the camera, and everything. But the force is weak. It's weak. So you don't notice that attraction. However, if you have a weak force, and then you have 6 million kilograms of material in the planet Earth, a weak force can be made up with a lot of mass. The more mass there is, the more pull. So when you take into account all the mass of the Earth, it adds up to a substantial amount. And if you add up the force between the sun and the earth, it adds up to a substantial amount. Okay, so weakness can be made up with in quantity. And it's always attractive. Any questions there? Yes, Aiden? I got your name now.
So is the pull of gravity the same for everything? Just if it has more mass, it is
The
stronger?
more mass, the more gravity.
Okay.
So that if you have, the easiest way to do it, the force, if I take the force between two of these, a specific distance apart, and then glue these together, the force between these and this is twice. If I put 2 over here, then it's going to be 4 times as much. So it depends on how much mass there is for each one, and also it gets weaker with distance. So as you separate between things, the force gets weaker with distance. But technically it never goes away. So technically we are attracted to galaxies that are trillions of billions of miles away. And in fact, galaxies orbit galaxies in the universe. So this gravity dominates the cosmos on the large scale. It's very, very weak, but when you have huge collections of mass, that makes up for it. And so then it becomes important. Now, we can ask something, because it's just doggone interesting. So it gets weaker with distance. You separate the objects, and the force gets weaker. So what happens when you bring them together? Get stronger. Okay? Get stronger. We don't have to go into the actual mathematical form of it. But aside from the fact that falling out of a tree or falling in general is bad, one of the things that happens as you get older, this is especially true of women, I don't know why, is that you lose bone mass and your bones get brittle. Little kids can fall because A, they don't weigh much, B, they don't have to fall very far. Big people like me weigh, 8 times as much as a kid. We're twice as high, so we fall twice as far. If we fall, it's easy to break an ankle, break a leg, break an arm, or whatever. Little kids, the first time you have a kid, you watch a kid fall, you go, and then you say, he's all right. Well, now, if a kid falls off a cliff, well, that's a different story. But little children are much more resilient. But when you get older, especially women, tend to lose calcium and their bones become brittle. What do we call that? Osteoporosis. And so what happens is you become susceptible to breaking something even in a simple fall. So you have to be very, very careful there when you get older. They have medications you can take to help build up your bones. And of course, eating lots of calcium and calcium-rich foods and exercising and so forth helps as well. So falling is a good reason for, is a negative part of gravity. Can you think of anything else that we wouldn't have if there wasn't any gravity? For instance, what has the Earth got that the Moon hasn't got and that Mars hasn't got? Air. Without gravity, there wouldn't be any air. The gravity holds on to the air here around the Earth. Okay? No gravity, no air. And if there isn't enough gravity and there is air, the solar wind can strip the atmosphere away. So we have enough gravity here on Earth to give us an atmosphere. All right? Is there any other day-to-day thing associated with gravity that can greatly affect things? Or does greatly affect things? You have to be a mariner or live near the ocean to be aware of this. What is it? The tides. The tides. You see, here's the Earth, and then here, a couple 100,000, 250,000 miles away, and this is not the scale, is the Moon. Now, you can show it with a computer or you can show it mathematically, but if there is a layer of water around, now this is greatly exaggerated, the water will bulge towards the Moon and also on the other side, so that the water will get pulled thinner, perpendicular and deeper on the side towards the moon and on the side away from the moon. Now, because the period of the moon is at 27.5 days, that could be in the exam, by the way, and the Earth rotates, it's 27.5 days, and you've got the rotation of the Earth, the time of high tide changes. But you're always going to have high tide when the moon is right straight up, or when the moon is at its highest during the daytime. Or, well, wherever the moon is, right below the moon, that's where you're going to have high tide, and on the other side of the planet as well. And so, as the moon moves around the planet, this bulge moves with the moon, and that causes the tides. In some places they can be very huge because of the shape of the bottom of the ocean, but the tides are tied to the motion of the moon, very much so. So it does have an effect. Gravity has a huge effect. We have the air. Well, of course, without gravity, what would happen to the water? It would be gone too, okay? There are also things that you don't think about on the space station. What do you do if there's a fire and you try to escape from a fire? Do you try to climb over the fire, or do you try to climb under the fire? You try to go under the fire, right? Well, guess what? If you have a fire in space, there is no up or down. Because the spaceship is really falling towards the Earth, the fire doesn't know which way to burn, and so in a zero gravity environment, which is a misnomer, there really is gravity, but it seems like it's no gravity. Fire burns down, up, left, and right. You cannot duck underneath a fire on the space station. Fire on a spaceship is very, very dangerous because there is no up in space, we should say, and therefore the fire doesn't know which way to go. It's terrifying. It's absolute. Of course, it burns up the air too. Also in space, where does all the dirt and garbage and all the other junk and the staples and all the other junk, where does it wind up in this room? Because of gravity. They don't sweep the ceilings, do they? What do they sweep? They sweep the ground. The dirt falls to the ground. You scratch yourself, skin cells come off, they fall to the ground. That's dust. Gross, but that's what it is. In space, it doesn't fall down. It just sits there and floats. So trying to keep things clean in a low G or microgravity environment is next to impossible. So it is kind of good that we have gravity. Okay, it certainly is. All right. Okay, that finishes what's on the test. Gravity will definitely be on there. So I hope our video viewers watch this today. I'll have it out there as soon as I can. And that brings us to the next idea. Now, before I plunge on, does anybody have any comments or questions? You're not holding, if you got a question, you're not holding the rest of the class back. You're actually helping if you ask a question. Well, the next great idea is arguably the most important idea we're going to cover, at least at this point in time. What's going on right now on the Gulf Coast? Who can tell me? I hope so. Yes, sir.
Hurricane Sally?
Hurricane Sally. And wasn't it just a couple weeks ago we had another hurricane? And there's another one called Teddy out there, and there's another one. And what's going on in California? Wildfires. The place is burning up. What's causing all of this? What's the problem here? Which our illustrious president, and I'll go on camera saying that, seems to think doesn't exist. What's going on here? Global, say it real loud, Aiden. Global warming. The planet is warming because sunlight comes in, and that is energy. We're going to be talking about energy. Energy is the next great idea. It's not going to be on this next exam, though. Sunlight is energy. It's radiant energy. When it comes through the atmosphere, it becomes heat, thermal energy. A lot of that heat goes back into space. It's radiated back into space. Thank God we have an atmosphere, because without the atmosphere it would be horrendously cold, aside from the fact that we couldn't breathe. All right? Just like your car gets very, very hot on a sunny day, the radiant energy comes through the window, gets converted into heat on the upholstery, and then it can't escape. It can't escape through the windows, and so the interior of the car can become stiflingly hot, to the point where it can kill a child or kill a pet. Never leave a child or a pet in a car with the windows closed. Never, ever do that. All right? You really shouldn't leave them there by themselves anyway, period, but closing the windows is asking for disaster. The same thing happens with the atmosphere. The sunlight comes into the atmosphere, gets converted into heat. The atmosphere is like a window. It lets some of that heat out, but not all of it, so that we kind of have a nice overall comfortable position for human beings. But over the last 400 years or so, 300 years, what have we been releasing into the atmosphere? Does anybody know what the primary gas is? It's carbon dioxide. And where does it come from? Fossil fuels. Burning coal, natural gas, oil, any of those things. When you release huge amounts of that kind of gas into the atmosphere, it tends to make it harder for the heat to get back out. And the result, the temperature of the planet is warming. That's changing the weather systems. It's changing where things are dry and where things are wet, and now we're paying the price. It's raising the sea level. Okay? Why do we burn the fossil fuels? Why do we burn gasoline? Why do we burn coal? Why do we do that? Well, where do you think the light comes from here? If you trace this light back, you're going to find it comes from a coal-fired power plant. Go out near California, it's coming from an oil-fired or natural gas-powered power plant. Some of it might be coming now from windmills, but most of it still comes from fossil fuels. We've burned so many fossil fuels because a fossil fuel is chemical energy. They are an energy source. And we have a ravenous appetite for energy in this country. It's one of those things, just like we have a much higher incidence of the COVID-19 virus, because frankly we've been stupid. I don't know what the fraction of our population is of the world, but we have 1/5 of the cases of COVID-19. Because of faulty government, faulty leadership, and equally as well stupid people who won't wear masks, who won't isolate, who won't do what they're supposed to. But let's go back to our energy usage, which is also excessively high. Why do we use so much energy? Why do we use so much energy? Well, we are encouraged to use energy. Who is encouraging us to use energy? Who are the people on the planet who are encouraging us to use energy? Don't make this hard. Do you think it's the energy companies? Yeah. The energy companies make money selling energy. We're going to show, just like it was difficult to prove that the Earth was not the center of the universe, we're going to show that energy cannot come from nowhere. All energy comes from someplace, and we need energy to survive. And since energy comes from someplace like coal, oil, natural gas, the energy companies are more than willing to dig it out of the ground and mine it or pump it or whatever and sell it to us. We're talking about trillions and trillions of dollars. And the more energy we use, the more money the energy companies make, and the higher the stock market. It's big, big, big business. Just to give you an idea, my electric bill is about $125 a month, and that's actually very low, because my wife and I, intentionally, we use quite a little bit of electricity. Okay, call it $100 a month. How much is that a year? $1,000, $1,200. Can you imagine $1,000 from every household in America just for the electricity? And how much do you spend on gasoline a year? Anybody bother to keep track of it? It's thousands. It's thousands. And people who heat their homes, I spend another $1,000 for heating oil. That's $2,000 that I spend, and it's just me and my wife, just me and my wife. Imagine $2,000 for every household in America. We're talking huge, huge, huge amounts of money to be made. And when they talk about the energy crisis, well, there are a couple of simple ways to cut energy usage and cut out the carbon dioxide emissions. One is there are too many damned people. There are too many people. Regardless of scriptures and what all the religious texts might say about going out and populating the earth, that was fine when those texts were written 1,000, 2,000, 3,000 years ago. It's not fine now. The planet cannot support this many people. In my lifetime, the population of the whole earth has doubled already. We are ruining the planet. And we are being encouraged to ruin the planet because money can be made by selling energy to us. So one way to help the global warming problem is to find other sources of energy. It's also to have fewer people, because fewer people will use less. But do the energy companies want us to have fewer people? Aiden? No. Why? More people means more energy, means more money. They could give a crap about the planet. They want us to use as much energy as possible. What else? How about changing how we live? It is shocking. You see people now they're so busy, they can't even find time to go to the grocery store to shop for their groceries. So we ship the food individually to each person in a giant cardboard container, all these food places that sell you stuff so you can cook at home. They generate tons of wasteful cardboard. They use up tons of energy in delivering all that food uselessly. Instead of having one truck go to the grocery store, we have 100 trucks driving all over. Yes? Oh, thank you very much. We'll stop there. But that's the point. We're going to talk about and prove that energy cannot be created or destroyed, and that it has to come from somewhere, and that has put us in this situation. Okay, let's do the quiz.